So, good afternoon, everyone. We'll start the session in 2 minutes. Okay, we'll start now. Let others join if in the meantime. Okay, I welcome you all for the week 6 for the NPTEL course problem solving session. So, the course is Computational Fluid Dynamics, and course instructor is Professor Sreenivas Jayanti sir from the Department of Chemical Engineering, IIT Madras, and myself, TA for this live session. And I am Ankara from the Department of Chemical Engineering, IIT Hyderabad. I am a research scholar. So, this is a, computational fluid dynamics course, which is basically a 12 weeks course. So, we have almost into halfway through the course. So, as we all know by now that we have seen like from the start with calculation of flow in a rectangular duct and triangular duct, and followed by that we have seen about the derivations of equations governing fluid flow, and later on it is about equations for incompressible flow and boundary conditions. And last week it was also about basic concepts of CFD like infinite difference approximations using stability, convergence, consistency, those things. And again this week it is about consistency, stability, and convergence. From the next week, what you will be studying is about solution to Navier-Stokes equations, which is basically what we require in any fluid dynamics problem. That is, in a cold flow system, we need to solve for the Navier-Stokes equations to get the variables like velocity, pressure, everything. So we'll see about that in the coming weeks, like a solution of Navier-Stokes equations for compressible flows and incompressible flows. And later on, it is about solution of linear algebraic methods by basic and advanced methods. And finally, it is about basics of finite volume method, including in grid generation and turbulent flows and turbulence modeling. So by now, we are almost clear of what we require from these computational fluid dynamics and what we are doing. What we are doing is nothing but we are solving for the system of equations to get the solution for that particular problem. So if pipe flow is our problem, we need to know what is the velocity at particular location, at pressure at particular location, or if there is heating involved, we need to know the temperature, those things. So if it is a pure cold flow system, we will be having continuity equations and three momentum conservation equations. In We will be solving those four equations to get the velocity and pressure fields. But if any additional things are happening inside the system, for example, if heat generation is happening or heat removal is happening, or any reaction is happening, we will be solving some additional equations for energy balance and mass conservation equations for those species involved in the chemical reactions as well. So all those things we have seen in the past weeks itself. So in today's class, we'll be seeing about the consistency, stability, and convergence and stability analysis methods, and general one-dimensional scalar transport equations. All those things will be we would not be going in theory behind the theory classes, because theory is already well established, well explained by the professor, and now we will be seeing problems related to all those concepts, so that it will be helpful for your assignment submissions. Because as you all know that your assignment counts towards certain 25%, I guess, best of 8 out of 12, and it will account for 25% of your final marks, I guess. So assignment submission is important, so this will be helpful when you are solving the assignments, and also it will be helpful for your final exams as well. Like it will help you clear out any doubts. So if you have any doubts, you can ask in between by stopping me, or you can ask at the end, whichever is convenient for you. So now moving on, we have five books for references. So first one is Ferziger Computational Methods for Fluid Dynamics, Springer, Berlin, Germany. And second, it is Hirsch Numerical Computation of Internal and External Flows, John Wiley and Sons, New York, USA. Third, it is Patanker SV, Numerical Heat Transfer and Fluid Flow, Hemisphere, Washington, DC. Fourth, it is Verstig Malalsegara, An Introduction to Computational Fluid Dynamics, the Finite Volume Method. And at last, it is Anderson JD Computational Fluid Dynamics, Basics with Applications. So now these are the 5 books. So now we will go on to week 6 problems. So again, as in previous classes, we have almost 20 problems. So we'll solve them step by step, and we'll see as we move on. So the first question, we'll see that it is about wiggles, stable spatial oscillations in regions of large gradients are an indication of what type of numerical error. I repeat, wiggles, stable spatial oscillations in regions of large gradients are an indication of what type of numerical error. So options are, three things are given. First one, it is diffusive. Second one, it is dispersive, and third one, it is truncation. So we are given three, and options below are a combination of these three, that is diffusive error, dispersive error, and truncation error. So basically, truncation error occurs because we are ignoring certain terms during the discretization step. So it doesn't account for the wiggles in regions of large gradients, so it is false. Now we have two things, that is diffusive error and dispersive error. So here it is mentioned that wiggles, that is stable spatial oscillations. So we must know whether it is due to diffusive error or dispersive error, or part of both. So in order to get to know that, we need to know what is diffusive error. Diffusive error is nothing but it is numerical diffusion. It occurs due to numerical diffusion or dissipation. So what happens is that it results in smudging of the parameters of the results, and therefore the amplitude or the waves will be reduced. And next is the dispersive error. So what is dispersive error is that appearance of the appearance of spurious oscillations or small wiggles is in the solutions. That is, these wiggles occur due to dispersive errors. So whenever it is resulting in the appearance of spurious oscillations, we call it, it occurs due to the dispersive error. So it basically results in different wavelength, and it is propagating at a different speed. And so it is like because of that phase error in waves, all those comes under the dispersive error. So here it is diffusive error is false and dispersive error is the right answer, because it is clearly mentioned that stable spatial oscillations, it is occurring because of the dispersive error only. Whereas diffusive error, it results in the smudging or diffusion or that dissipation. Those things occur because of the diffusive error. So our answer is option 2, that is dispersive error. So option A, it is 1. Option B, it is 2. Option C, it is 1 and 2. Option D, it is 1, 2 and 3. So we know that the answer is option B, that is 2. Dispersive error is the right answer. Option B, 2. So now we'll see a quick explanation for that. So it is that diffusive errors lead to a smoothing of the solution and a gradual loss of sharp features and not oscillations. So as I mentioned, it leads to that diffusion and it leads to smoothing of the solution and therefore a gradual loss of sharp features. And dispersive error, as we have seen, that it causes oscillations or wiggles, especially in regions where there are steep gradients or sharp changes in the solution. So our answer is dispersive error. And truncation errors are errors that occur due to the approximation of the exact solutions and they don't specifically cause oscillations. So although they might lead to other type of numerical instability. Truncation error can lead to instability, but that is not what is asked in the question. In question, it is specifically about oscillations or wiggles. So the right answer is dispersive errors. Now moving on to how we can reduce this dispersive error is that we can actually minimize the grid spacing. So refining the spatial discretization, that is making the grid size or the mesh size finer, results in less numerical dispersion error. So on a thumb rule is that grid step size should be 1/10 of the, sorry, not 1/20th of the wavelength of the material, and these things can help like reducing the grid size, those things. So now we'll go to question 2. In question 2, what is asked is that von Neumann stability analysis is restricted to dash. Von Neumann stability analysis is restricted to dash. So things given are, first one, it is linear initial value problems, and second it is periodic boundary conditions, and third it is linear boundary value problems. So von Neumann stability analysis is restricted to dash. So actually von Neumann stability analysis is restricted to linear initial value problems and periodic boundary conditions. So first two are the answer and third one is false. It is not it is not for the linear boundary value problems. So we'll look at the options first. Option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 1. Option D, it is 1, 2 and 3. So von Neumann stability analysis is restricted to linear initial value problems and periodic boundary conditions. So the right answer is option A is the right answer. Option A, 1 and 2. So why is that? Von Neumann stability analysis, it is a method used to assess the stability of the numerical schemes, particularly for the partial differential equations. So here also in our case, we are using the von Neumann stability analysis to get the stability of the system, to know when the system will be stable when we are dealing with the partial differential equations like continuity equations, momentum conservation equations, or like those things. So it is typically restricted to linear initial value problems and periodic boundary conditions. So linear initial value problems, now von Neumann stability analysis is designed for problems where system is linear and can be expressed in terms of wave-like solutions. It assumes that the error propagates in a linear manner which allows for a simplified analysis. So mostly it is like used for the linear problems and it assumes that error propagates in the linear manner. So it simplifies the analysis, and therefore it is used in those cases. So with one criteria we can't analyze the stability for all the systems that we are using. So it is one of the method, and it is used for the linear initial value problems and periodic boundary conditions. So periodic boundary condition, this analysis assumes the periodic boundary conditions, which again simplifies the problem because the solution itself repeats at the boundaries, avoiding complications from non-periodic boundary conditions. So what happens in periodic boundary condition is that we give a repetition of the values at the boundaries, like different boundaries we can connect and we can give the values. So it complicate, I mean it less lowers the complication arising from using non-periodic boundary conditions at all boundaries. So third one, it is linear boundary value problems. While this analysis is generally used for linear problems, it is specifically designed to handle initial value problems with boundary conditions. That is, von Neumann stability analysis is highly limited to linear initial value problems and periodic boundary conditions. For boundary value problems with more complicated conditions, von Neumann stability analysis is not typically directly applicable. So again, going back to the question, what is asked is that von Neumann stability analysis is restricted to dash, and answers are linear initial value problems and periodic boundary conditions. So option A, which is mentioning 1 and 2 as the right answer, is the right one, because von Neumann stability analysis doesn't deal with linear boundary value problems, and we are limited to linear initial value problems and periodic boundary conditions. So that is the answer for question 2. Now we will move on to question 3. In question 3, it is asked that which of the following does not affect stability of a hyperbolic problem. I repeat, which of the following does not affect stability of a hyperbolic problem? And options, I mean, we are given few things. First one, it is mesh spacing delta x, and second one, it is velocity, and third one, it is viscosity, fourth one, it is time step delta t. So in question it is asked about which of the following is the not affecting the stability of a hyperbolic problem. So when we look at it, hyperbolic problems, we can see that it is some varying with respect to time as well as the position. So we need to know that we need to have a certain stability criteria. So for example, if it is a Courant CFL number, that is Courant Flichen something. Once again, I'll just check and let you know. It is Courant, Friedrich and Louis CFL numbers. So like those things, we have a certain criteria to get to know the stability of the problems. So what those numbers or those condition depends on is that it depends on velocity, it depends on time spacing, it depends on mesh spacing, and depends on time stepping. So if we take Courant number itself, it mostly will be a function of velocity delta t delta x. So and we will put certain condition such that the Courant number must be less than this value. Like that we will be giving certain condition. Why it is like mostly it will be like v into delta t by delta x, and powers may vary. So what we are trying to give is that how much, with what speed the information is being transferred across the cells, across the grids at with respect to time as well. So if it is traveling fast, or if it is traveling a far distance, we will be missing out certain information. So the systems will go unstable. So that is how we control the stability of a system using Courant number and all. So here it is asked that which of the following does not affect the stability of a hyperbolic problem. So a hyperbolic problem generally involves variation with respect to this time and position as well. So we need to take into account mesh spacing. Yes, it affects the stability. And second, velocity. Again, velocity affects. Third, viscosity. Viscosity doesn't affect in the stability of a hyperbolic problem. So third one is a false, and fourth one is time step. Again, delta t plays a major role over here. So 1, 2 and 4 is the right answer. That is mesh spacing, velocity and time step affects the stability of hyperbolic problem. But we need to read the question carefully. Here answer is not 1, 2 and 4. What is asked in the question is that which of the following does not affect the stability of a hyperbolic problem. So does not affect is that viscosity does not affect the stability of a hyperbolic problem. So all these things affects, but viscosity does not affect. So when you are reading the question, please read the question carefully, otherwise we might miss out what is being asked. So and we might go into some other assumption. So yeah, which of the following does not affect stability of a hyperbolic problem? Answer is viscosity. So option 3 is the right answer. We'll look at it. In option A it is given 1 and 2. Option B 3 and 4. Option C 3. Option D 2. So here it is mesh spacing is affecting, velocity is affecting, viscosity is not affecting, and time step is affecting as well. So 3 is the right answer, which is given from option C. So option C is the right answer. I hope it is clear. While reading the question, take 1 minute and understand what is being asked and don't confuse yourself. So we'll move on to next question now. In the next question, what is being asked is that stability is a problem of the dash. Stability is a problem of the dash, and options given are differential equation, difference equation, computer accuracy. So stability is a problem of dash, differential equation, difference equation and computer accuracy. So we'll look at the options first. Actually, it is a problem of all actually differential equation, difference equation, and computer accuracy. So we'll see the options first. Option A 1, option B 2, option C 3, option D 1, 2 and 3. So the right answer is actually option D, which is implying that 1, 2 and 3 is the answer. So what exactly it is asked in the question, we'll see. Stability is a problem of the dash. So stability is nothing but with the exact solution of the discretized equation and the computed solution remains like or close enough. So that is what is given by the stability, I mean given from the stability. So it puts some constraint that we will get the solution from this if the system is stable. If it is unstable now, like we will be having a large error, and the error keeps on multiplying. So it is that stability is that where the exact solution of the discretized solution and the computed solution are like close enough. So if the system is unstable, what will happen? The computed solution will be deviating far from the exact solution, and therefore we will be having issues. So it is option D. It is a problem of differential equation, and it is a problem of computer accuracy, and it is a problem of difference equation. So 1, 2 and 3 is the right answer. Answer option D. 1, 2 and 3. So now we will go to question 5. In question 5, what is asked, we'll see. If wiggles appear in numerical solution, then what can be done to eliminate them? If wiggles appear in numerical solution, then what can be done to eliminate them? So options, first one, it is decrease the time step. Second one, decrease grid spacing. Third, use more accurate scheme. So we have seen what wiggles are and when it will appear in the first question itself. So in the first question we have seen that wiggles are caused due to the dispersive error, that is these stable spatial oscillations are caused due to the dispersive error, and it is because of the appearance of these spurious oscillations or the wiggles in the solution, and it occurs by propagation of the different wavelengths at different speed, and it that time itself we have seen that how to minimize that numerical dispersion error. We need to refine the spatial discretization, we need to reduce the grid size, we need to reduce the spacing between the grids. So option 2 is the right answer, that is decrease spatial grids, decrease grid spacing is the right answer. So we will look at the options first and we will see. If wiggles appear in a numerical solution, then what can be done to eliminate them? We can eliminate them, we can reduce them by decreasing the grid spacing. So options are option A 1, option B 2, option C 3, option D it is 1 or 2 or 3. So answer is option B, that is decrease grid spacing is the right answer. And if we are decreasing the grid spacing, actually a time step also needs to be adjusted according to the grid spacing, because then CFL number condition, those things will be there in any system. So we need to be conscious in while decreasing the grid spacing also. So next, answer is option 2, that is decrease grid spacing. If wiggles appear in numerical solution, then what can be done to eliminate them? So answer is decrease grid spacing. So it is given by option B. Option B 2, that is decrease grid spacing is the right answer. So now we will go to the next question. In question 6, what is being asked is that which of the following is false about the Quran number? Which of the following is false about the Quran number? So Quran number is also known by CFL number. CFL is nothing but Quran, Friedrich and Louis. So CFL or Quran number, it helps us to identify the rate at which the information is being passed across the grids at with respect to time as well. So mostly it will be v into delta t by delta x, v into delta t square by delta x square, something like that. So which are the following is false about Quran number? So we need to identify which of the following statements is false. Again I am highlighting, whenever you are reading the question, please read the question very consciously. So now we will see the options, the different things first. So first one, it is Quran number is a condition on the stability of a numerical scheme. So is this statement true? Yeah, Quran number is a condition on the stability of a numerical scheme. This statement is true because what it is stating some stability criteria. Like if v into delta t by delta x is less than something, it means that a system is stable. Mostly when we are dealing with pipe flow or some for water alone, let us keep, we will be giving that Quran number should be less than 1. So what it means is that delta v, so not delta v, v into delta t by delta x should be what to say, should be within that 1. So if it is within that 1, right, what happens is that velocity is passing with the velocity is like into delta t by delta x, value is within less than 1. So if it is less than 1, the system will be stable. But if it is greater than 1, right, what is being affected there? It mostly we are almost fixing delta t and delta x. So what will vary? Velocity will vary. Velocity will keep on increasing and the system will become unstable. Like velocity keeps on increasing and everywhere it happens and we cannot get the solution to that system. So Quran number is a condition on the stability of a numerical scheme. So when we are specifying Quran number, we are imposing that it should be less than some critical value, and that value let us know at which speed the information is being transferred across the grids. So if it is like if value is not contained within that Quran number, the system will become unstable. So we say that Quran number is the condition on the stability of a numerical scheme. So first statement, it is true. Now we will move on to second statement. High value of Quran number is desirable for consistency. So as I mentioned that high value of Quran number is not desirable for consistency. So why is that? Because it high value of Quran number basically means that V into delta t by delta x. So in such cases what happens? V is becoming very high. So when it happens, right, v into delta t by delta x, if time step is fixed, it will be like only v will vary and the system will the solutions will diverge actually and we will not get the solution. It will be very high. It will lead to very unrealistic values if Quran number is very much higher. And also it is like if this will be the case, that is velocity keeps on increasing, when Quran number criteria cannot be met, it will then diverge, the solutions will diverge. But if we are varying time step also, like we are giving that delta t is not fixed, rather delta t will be calculated based on the present condition of the system. If such cases is given, what happens is that delta t value will go on becoming very low. It will go to 10 power minus 23, 10 power minus 50, something like that. And again, it is physically unrealistic values we will be getting. So high value of Quran number is actually undesirable. It is not required at all. So second statement is the false statement. Now out of 1 and 2, we know that 1 is true, 2 is false. Now we will see next statement. Quran number condition does not arise for elliptic problems. So this statement is actually true because elliptic problems will be of the state delta square u equal to 0. Like those what we call like elliptic problem or just a minute. Yeah, that Laplacian equation, Poisson equation. Yeah, Poisson equation, Laplacian equation, all those are examples. So there actually speaking, Quran number condition does not arise. We will see why in the next slide, but to give you an idea, it is a time independent solution, all those elliptic value problems. So third statement is again true. Now, coming back to the question we are asked to identify which of the statements are false. And first statement is true. Quran number is a condition on the stability of a numerical scheme, true. Second statement, high value of Quran number is desirable for consistency. It is false. High value of Quran number is not desirable for consistency. And third, it is Quran number condition does not arise for elliptic problems. Again, this is a false statement because Quran number condition arises for elliptic problems. Sorry. This is a true statement. Quran number condition does not arise for elliptic problems. This is a true statement. Why we will see in the next slide actually. But out of all the options, only second is false. Rest are 1 and 3 are true. Option A 1 only, option B 2 only, option C 3 only, option D 1 and 3. So answer is option B, that is 2 only is the right answer. Answer is option B, that is 2 only. So now we will see why that is the case. In the question, what is asked is about Quran number. So Quran number decides how much information travels across the computational grid in time. So in that particular time interval, how much information is being transferred across the time computational grid. So it depends on velocity delta t delta x actually. And elliptic problems is given in this format, that is delta square u equal to 0. Here instead of u you can keep f if you want the equation to be very generic. And we are just discretizing the equation, the Poisson equation and Laplacian equations. Those LHS side looks something like this: dou square u by dou x square plus dou square u by dou y square equal to 0. So here we are having those diffusive terms. So the solution to this particular equation is independent of time. It is not varying with respect to time, and we need to solve the solution simultaneously at all the grid points. So elliptic solution is actually independent of the Quran number. So option B is false. B is for 2 is false and 3 is true. It is independent of the time step, and it is Quran number condition does not arise for the elliptic problems. And also Quran number value should be not be high. It should be low and it should be within certain bounds. So that is for question 6. So now we are almost into question 7. In question 7, this is the figure given. We'll observe the figure first. And the description for the figure is also given below. So what happens is that the initial condition that is this solid line, that is blue color line, is the initial condition, and the computed solution, that is these points, this red color, violet color and green color, all those points are the computed solutions at 3 different times. So it is at the 0 condition, and it is at almost 0.1, it is 0.2, and it is almost 0.5. So initial condition and computed solution at 3 different times for one dimensional unsteady case. So it is a one dimensional problem and it is unsteady case. So as we are also able to see, it is varying with respect to time. So we call it unsteady solution. And initial condition is given and computed solution at 3 different times are given. And here in the y-axis we have velocity, that is u. This is a function of time as well as position, and in the x-axis we have time. Now we will see the question. Identify the wrong statement. We need to identify the wrong statement. If the computed solution in figure 1 is for unsteady wave equation, so here already it is mentioned that it is about the unsteady equation, unsteady case. So if the computed solution is for unsteady wave equation, so we need to identify the wrong statement. First one, numerical error is said to be diffusive. Numerical error is said to be diffusive, And second one, numerical error is said to be dispersive. So numerical error is said to be diffusive and numerical error is said to be dispersive. Out of I think only two statements. Out of these two statements, we need to identify which of these are false or wrong statements. So what is given, numerical error is diffusive or numerical error is dispersive. The question is simply that only. We need to identify the type of error. So when we look at this figure, right, what we are able to see, we are not seeing any oscillations. Appearance of oscillations indicate it is a dispersive error, whereas appearance of diffusion, that is smudging of the edges or reduction in the amplitude, those things are associated with the diffusive error. So we have diffusive error and we have dispersive error, and appearance of oscillation indicates dispersive error, whereas appearance of diffusion, that is smudging of results, indicates diffusive error. So when we look at this figure, we are able to see that the result is diffused and amplitude reduction is also observed, but we are not able to see any oscillations here. So it is not dispersive error, it is a diffusive error. So in the question, but we are asked to identify the wrong statement. We are not asked to identify the correct statement, but rather we are asked to identify the wrong statement. So when we say that, if we put true or false, we are able to see that it is a diffusive error with respect to figure 1, and it is a it is not a dispersive error. So one is true, second is false. But since we are asked to identify the wrong statement, our answer is option 2. That is, the numerical error is said to be dispersive. So option 2 is the right answer. We'll look at the options first. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Oh, sorry. Option D, neither 1 nor 2. So answer is option B, that is 2 only is the right answer, because first one is a true statement. Answer is option B, that is 2 only. Two only is the right answer. Option B is the right answer. Now we are looking at question 8. In question 8, what is given? For the one-dimensional wave equation, which of the following is true for FTBS explicit scheme? Forward in time, backward in space, explicit scheme. So again I read the question. For the one-dimensional wave equation, which of the following is true for FTBS scheme, explicit scheme? So given in options, given things are, first one, it is first order accuracy, second one consistency, third one conditional stability. For the one dimensional wave equation, which of the following is true for FTBS explicit scheme? So basically, if we look at it, right, it is for FTBS is first order accurate, and second one, it is consistent, and it is conditionally stable. So all three are true actually. First order accurate, consistent, and conditional stability, all three are true. So we look at the options. First, option A, it is 1. Option B, 1 and 2. Option C, 1 and 3. Option D, 1, 2 and 3. For one dimensional wave equation, which of the following is true for FTBS explicit scheme? So 1, 2 and 3 is the right answer. Forward, first order accuracy, consistency, conditional stability. So 1, 2 and 3 is the answer. Option D is the right answer. Now, when we look at it, FTBS, forward time backward space explicit scheme on the one-dimensional wave equation. So it is first statement given is first order accuracy. FTBS is generally first order accurate in both time and space, that the truncation error is proportional to delta t and delta x. So we call it as the first order accurate in space as well as time. And second was given consistency. FTBS is consistent. This means that as delta t and delta x approach 0, numerical scheme approaches the original partial differential equation. So first order accuracy implies consistency. So as delta t and delta x approaching 0, numerical scheme approaches the original PDE, and therefore we can say that it is a consistent scheme. And last one, it is a conditional stability. So we sometimes say that the equation is stable under few conditions, and it is some equations will be unconditionally stable. For example, implicit schemes mostly will be like unconditionally stable. They would not be depending on the time step values or grid spacing values. So we call them as unconditionally stable. But whereas most of the explicit schemes will be dependent, their solutions and the stability will be dependent on delta t and delta x. That is, it depends on the time step as well as the grid spacing. So FTBS is a conditional stable, it is conditionally stable. For the wave equation, explicit schemes like FTBS have a Courant-Friedrich-Lewis condition, and it must be, the system must be must satisfy the CFL condition to get the stability. So this condition relates the time step, spatial step and wave speed. That is, the CFL is equal to V into delta t by delta x. It is not always directly proportional. I mean, sometimes it would be delta x square, sometimes delta t square. So those things will come into picture depending on the equations which we are dealing with. But in general case, it would be like V into delta t by delta x, or you can consider it as directly proportional to time step and inversely proportional to the spatial step and directly proportional to the velocity. So it must satisfy conditions like CFL number for the system to be stable. So it is a conditionally stable. If the CFL condition is not met, solution will likely become unstable and diverge. So if CFL condition is not met, what will happen? The solution will likely become unstable and it will diverge. So answer is first order accurate, consistency, stability, conditionally stable. So all three are right ones. So FTBS, that is forward time backward space explicit scheme on one dimensional wave equation, is first order accurate, consistency and conditional stability. So that is for question 8. Now we will go to question 9. In question 9, what is asked is that which of the following schemes is unconditionally stable for the unsteady diffusion equation? I repeat, which of the following schemes is unconditionally stable? So the last slide only we have seen that when the system is conditionally stable and when it will be unconditionally stable. So most explicit schemes will be like conditionally stable. Like if it obeys this particular condition, it will be stable. If it doesn't obey, it will move to unstable. It will become unstable. But most implicit schemes will give rise to unconditionally stable systems. That is, we need not fix the delta t. So what basically CFL criteria states is that we know we have velocity, we have delta t, we have delta x, right? So we are saying that it should obey CFL condition. We should obey it should obey CFL condition. So what it means is that we need to adjust the delta t and delta x in such a way that CFL condition is met. So we can say that we have a hold on the parameters like delta t and delta ix for us to get a stable solution. So in all cases, it becomes very difficult. Mostly time step value is the one which is highly impacted. We need to keep it very low in such cases. So explicit scheme wherever we are using, we will be having a very low time step. So system will take a lot of time to get the solution. So delta t is uh, delta t is becoming very low as a result of that. So that is what we call it as a conditionally stable. We are having some conditions and we are changing delta t to make sure that condition is being met. That is the meaning. Now when we are saying unconditionally stable, we cannot keep, we need not keep such low time step values. So we can go ahead with a normal range and we can get the solution. So that is what we mean by unconditionally stable. Because the system is unconditionally stable, we need not have strict criteria for the time step and all. So which of the following schemes is unconditionally stable for the unsteady diffusion equation? Sorry. Which of the following scheme is unconditionally stable for the unsteady diffusion equation? So we will see that first one it is FTCS explicit and second one it is Crank-Nicolson scheme. So mostly it is FTCS explicit is like explicit scheme and it is a conditionally stable scheme. The most conditional stable condition will be like CFL number. It would be like alpha into delta t by delta x square must be less than or equal to 1 or must be less than or equal to 0.5. Such things will be there. But mostly since it is an explicit scheme, we can say it is a conditionally stable. And second one, it is a Crank-Nicolson scheme. And Crank-Nicolson scheme, it is like it actually in the implicit scheme, and it is having a combination of in the time stepping schemes. So we can call Crank-Nicolson scheme as unconditionally stable scheme. Mostly it is like implicit only, so if we need not impose strict condition on the time stepping. With the normal time stepping itself, normal time step size, we will be able to get the solution. So option 2 is the right answer. We'll see that first one, option A 1 only, option B both 1 and 2, option C neither 1 nor 2, and option D 2 only. So unconditionally stable system is Crank-Nicolson system. FTCS is conditionally stable system. So answer is option D, that is 2 only is the right answer. Option D 2 only is the right answer. Now we will go to question 10. In question 10, what is given is that unsteady one-dimensional advection equation with diffusion is given by dash. Unsteady one-dimensional advection equation with diffusion is given by dash. Option A, dou f by dou t equal to dou f by dou x. Option B, dou f by dou t plus dou u by dou x plus dou v by dou y equal to 0. Option C, dou f by dou t plus dou f by dou x plus dou f by dou y equal to 0. Option D, dou f by dou t plus dou f by dou x equal to dou square f by dou x square. So we have 4 things and we need to identify which of the following 4 are unsteady one-dimensional advection equation with diffusion. So we need to read these questions carefully. What is asked? The system is unsteady and it is a one-dimensional system, and we have advection equation as well, and we have diffusion term as well. So this is 4 things must be satisfied in the equation, and which of the following is such equation? So if anyone of you wants to answer, you can answer actually. Okay. We'll see the question. That is, as I mentioned, it is equation should satisfy four things. It should be unsteady equation, it should be a one dimensional equation, it should be an advection equation, it should have diffusion component as well. So we'll see the first option, that is dou f by dou t equal to dou f by dou x. That is, this system is unsteady system because the parameter is varying with respect to time, and it is having advection term as well, dou f by dou x, but it doesn't have the diffusion component. So this statement is false statement. Next, I mean, this equation is not exactly replicating what is given in the equation and given in the statement. So A is the false. Now coming to B, we have dou f by dou t plus dou u by dou x plus dou v by dou y equal to 0. And if we look at it, we have unsteady component dou f by dou t. Next one, if we look at, we have dou u by dou x plus dou v by dou y equal to 0, and it is mostly of the continuity equation. We can call, like, take it as an advection, but here the variation is with velocity, so it is not exactly related to our question, and also it is a two-dimensional. We have x dimension and y direction as well, so it is a two-dimensional problem. So again B is false. Now coming to C, we have dou f by dou t plus dou f by dou x plus dou f by dou y equal to 0. We have unsteady component. We have the advection component, but it is a two-dimensional problem. Dou f by dou x plus dou f by dou y. We have x dimension and y as well. So it is a two-dimensional problem. So again, third option C is false. If we go and look at option D, we have dou f by dou t plus dou f by dou x equal to dou square f by dou x square. So we have only x component, that is x dimension, we have x, and we have unsteady component as well, dou f by dou t. It is varying with respect to time, and we have advection term as well, dou f by dou x. It is varying with respect to position, and we have diffusion term as well, dou square f by dou x square. It is diffusing. The term diffusion term is also there, advection term is there, and it is an unsteady equation, and it is a one dimensional equation. So all things are satisfied in option D, that is fourth equation. So answer to this question is option D is the right answer. Answer is option D, that is dou f by dou t plus dou f by dou x equal to dou square f by dou x square. System is unsteady system with advection, one dimensional advection equation with the diffusion. So it is I mean, it is satisfying all things, and also it is a one dimensional equation. So now we will go to next question, that is question 11. In question 11, what is asked? Which of the statements is correct about discretization of the one-dimensional unsteady diffusion equation? Which of the four statements is correct about discretization of the one-dimensional unsteady diffusion equation? We will see the options. Options are, statements are consistent and unconditionally stable schemes can be developed. And second one, FTCS scheme is conditionally stable. Okay. Now what we having is that we are having a statement about discretization of one-dimensional unsteady diffusion equation. One-dimensional unsteady diffusion equation, and we need to identify which of the statements given are right and wrong. So first statement is consistent and unconditionally stable schemes can be developed, and second one it is FTCS scheme is conditionally stable. So actually speaking, both the statements are correct over here. We can develop consistent and unconditionally stable scheme as well, but when we are using FTCS scheme, it is conditionally stable. So both the things are true. We'll look at the options now. Options are option A 1 only, option B 2 only, option C both, option D neither. Yeah, you can. Do you have any question? You can. Could you please say 10th answer again? Okay. And like we are asking about unsteady one-dimensional advection equation with diffusion is given by dash. I mean it is given by which of the equations? So first it is one-dimensional equation. So what are all the parameters we have? It will be varying with respect to x only, and y and z, those directions, I mean variation in those dimensions will not be there. So second and third options are wrong. And unsteady equation, so it is dou f by dou t, it is varying with respect to time, so that term will not vanish. So unsteady one dimensional advection equation with diffusion, so here dou square f by dou x square is there, and it is mentioning about it is including the diffusion. So diffusion, viscosity, those things in Navier-Stokes equation, right? It is like momentum transport due to the diffusion. So it is there we give dou square u by dou x square. So those terms due to diffusion, variation because of the diffusional effects. So we give in this particular format, that is dou square f by dou x square. So f here is some generic term. It can be u, it can be t, whatever. But here we have unsteady one dimensional equation, so it is dou f by dou t plus dou f by dou x equal to dou square f by dou x square. It is unsteady, it is having advection, that is dou f by dou x. We have in dou u by dou x, something like that, right? And dou square f by dou x square, so it is a diffusion term. So our answer is option D, that is dou f by dou t plus dou f by dou x equal to dou square f by dou x square, which is satisfying the unsteady term, which is satisfying the advection, which is satisfying the diffusion, and also the equation is one dimensional equation with respect to x alone. So that is the thing. Okay, yeah, thank you. Now we will go to question 11. In question 11, what is asked is that which of the statements is correct about discretization of one-dimensional unsteady diffusion equation. So first statement, it is consistent and unconditionally stable schemes can be developed. Second statement, it is FTCS scheme is conditionally stable. So as we mentioned already, it is like consistent and unconditionally stable schemes can be developed. If implicit schemes mostly will be like unconditionally stable, but also will be consistent in their solution and will get a converse solution at last. Similarly, explicit schemes or FTCS schemes, some schemes will be like conditionally stable. So for the given one dimensional unsteady diffusion equation, FTCS scheme is conditionally stable. It is like again dependent on Courant number criteria, which is a factor of delta t by delta x. So it is conditionally stable. Similar way, we can develop schemes using consistent and unconditionally stable schemes. So it is like implicit scheme. Implicit scheme is that uh, like mostly it would be like averaging across with respect to time. So we will be solving at all the equations simultaneously and we will get the solution. So implicit schemes are preferred in most cases compared to the explicit schemes, but explicit is conditionally stable and implicit is unconditionally stable. So talking about the one-dimensional unsteady diffusion equation, we can get we can get unsteady not unsteady, we can get unconditionally stable schemes which are consistent as well. It can be developed, and similarly, but when we are using FTCS, it is a conditionally stable system. So 1 and 2 both are right. So coming and looking at the options, we have A 1 only, B 2 only, C both, and option D it is neither. So answer is option C is the right answer, that is both. Option C is the right answer. So first unsteady one-dimensional diffusion equation is given by this. Dou F by dou T equal to A into dou square F by dou X square. And we have dou F by dou T minus A into dou square F by dou X square equal to 0. We are just taking it to the other side. And FTCS explicit scheme, it is forward time and central in space. So what we are doing, we are just discretizing it. It is Fi, we are keeping forward in time. So we are using n plus 1th time step and nth time step. So n and n plus 1th time step divided by delta t. On the this is forward in time, and central in space we have a into f I plus 1 at nth time step minus 2 fi at nth time step plus fi minus 1 at nth time step divided by delta x square. So here it is variation with respect to time, here it is variation with respect to space, that is I plus 1 I and I minus 1, so delta x square. So this is the FTCS explicit scheme. So here if we take fi n plus 1 equal to a into delta t divided by delta x square, and we are keeping the rest of the terms constant, and this fi at n goes to the other side. So what will happen, f at fi at n plus 1th time step equal to fi at nth time step plus a into delta t by delta x square into all these terms, f at I plus 1 at nth time step minus 2 times of fi at nth time step plus fi minus 1 at nth time step. So now what we are doing, we are just taking everything, sigma is a into delta t by delta x square. So sigma we are taking like common, and we are writing the equation fi at n plus 1 is equal to sigma into fi plus 1 n minus plus 1 minus 2 times of sigma. So here 2 times of sigma and 1 will be coming from this particular term. So 1 minus 2 times of sigma into fi at nth time step, fi at nth time step, plus again sigma f at I minus 1 at nth time step. So this equation we will be getting. So this sigma equal to a into delta t by delta x square. So here we are giving this factor is what we are taking it as a common, and this denoting as sigma. So sigma equal to a into delta t by delta x square. So mostly we will be having criteria such as this sigma should be less than or equal to 0.5. So a into delta t by delta x square should be less than or equal to 0.5. So this is the condition. So if this condition is satisfied, we will get a stable solution. But if this condition is not satisfied, the solution will be unstable. So we should adjust our delta t and delta x in such fashion. So that is the thing. So FTCS is a conditionally stable scheme. Similarly, we can this is a conditionally stable scheme, and when we are using implicit scheme like Crank-Nicolson scheme, it is unconditionally stable and also consistent. So both the statements are true. Consistent and unconditionally stable schemes can be developed, but this is true, and also FTCS scheme is conditionally stable. So this statement is also true. So both of them is the right answer. Now we'll go to question 12. In question 12, what is asked is that which of the following numerical schemes is not preferred for the numerical solution of a PDE? Which of the following numerical schemes is not preferred for the numerical solution of a PDE? So that is when we are solving the partial differential equation, which of the schemes are not preferred? So first one, it is consistent but unconditionally unstable scheme. Second one, inconsistent but conditionally stable scheme. And third one, it is consistent but conditionally stable scheme. So what is being asked in the question is, we need to identify the numerical scheme which is not preferred for the numerical solution of a PDE. So we are given three statements. First, let us identify what is preferred and what is not preferred. So first statement is stating that consistent but unconditionally unstable scheme. So this scheme is consistent but it is unstable, like it is unstable. So would we prefer that? We would not prefer that, right? In the last class only we have seen about the lax equivalence theorem. So what was lax equivalence theorem stating? It was stating that consistency and stability are two criteria which when satisfied we will get the convergent solution. So basically we need a system that is consistent and it should be stable. Stability and consistency is must. Only then we will get the converged solution. So while we are solving for the numeric partial differential equation, our ultimate aim is to get the converged solution. So the solution should be consistent as well as stable. Both of them are preferred. So when we are looking at the option 1, that is statement 1, what it is stating is that consistent but unconditionally unstable scheme. So it is unstable, so it is not preferred. 1 is not preferred. Second one, again it is inconsistent but conditionally stable scheme. So second one is also it is like inconsistent scheme, but it is a conditional stability under particular condition like a CFL number. So those conditions, it is stable. So system is stable. We can take it as a system of stability, but it is inconsistent. So we would not prefer it as well. So first one is also not preferable. Second one is also not preferable. So third one, it is consistent but conditionally stable scheme. So the third one, what it is given, it is a consistent scheme but it is a conditionally stable scheme. But it is fine as long as we are satisfying the condition, we are getting a stable solution, it is fine. So we can prefer that third scheme, consistent but conditionally stable. It is consistent and the system is also stable. Even though it is under certain condition only the system is stable, but it is a stable system. So we can say that consistent and stable schemes, it will lead to convergent solution. So third one, it is a preferred one. So in the question we are asked to identify which of the following schemes is not preferred. So answer is 1 and 2. We will look at the options. Option A, 1 only. Option B, 2 only. Option C, 3 only. Option D, 1 and 2. So we know now that it is answer is option D, that is 1 only is the right answer. Sorry, option D, 1 and 2 only is the right answer. 1 is not preferred. Similarly, second statement is also not preferred. Why? Because for the system to get converged solution, we need it to be consistent and stable. That stability can be conditionally stable or unconditionally stable. That doesn't matter, but it is, yeah, but it is like it should be satisfying consistency and stability for us to get a converged solutions. So one and two statements doesn't make true of that. One is consistent but not stable. Second is inconsistent but stable. So both of them are not preferred. So answer is option D. That is 1 and 2 is the right answer. Option D. Option D, 1 and 2. Now we will go to question 13. Now we are looking at question 13. For question 13 we have one figure. So in this we are able to see one straight line and one dotted line. So we look at the question first. Okay, this is figure 2 and it shows the exact solution. So figure 2 shows the exact solution, that is solid line, and the computed solution dotted line as a function of x at a particular time instant. Difference between the two is attributable to the truncation error in time and space. True. Okay. Figure 2, that is this figure, is having the exact solution is this, and the computed solution, that is dotted line, is this, and it is a function of x, and this particular thing is with respect to some at some particular time instant. So we have a difference between the two schemes, I mean two lines, that is we have difference between the exact solution and the computed solution, that is it is not exactly matching. The difference between two is attributable to truncation error in time and space. Option A true, option B false. So we have variation with respect to position as well. Like here it is with respect to position, if we see it is varying, and also with respect to time also it is varying. Like so we can say that difference between two is attributable to truncation error in time and space. So answer is option A, that is true is the right answer. Now let us go to question 14. In question 14, what is asked is that for the one-dimensional wave equation, which of the following is true for FTFS explicit scheme? For one-dimensional wave equation, which of the following is or are true for the FTFS explicit scheme? So what is FTFS? FTFS is forward in time and forward in space, and it is explicit scheme. So what comes to our mind is that if it is an explicit scheme, we will be having conditional stability mostly. It can be like unstable also sometimes, but you need to check that. But mostly it will be conditionally stable only. We'll see what is given. First one, it is first order accuracy. Second one, inconsistency. Third one, unconditional stability. Okay. For one-dimensional wave equation, which of the following is or are true for the following for the FTFS explicit scheme? So first one, it is given that it is a first order accuracy. and second one it is given that inconsistency, and third one it is unconditional stability. So mostly FTFS, forward in time, forward in space, is first order accurate, because we are using forward in time and forward in space. Mostly that will be first order accurate only. We'll see that in the next slide actually. And it will be consistent actually, it won't be inconsistent. And consistent is nothing but when we are reducing the time step and grid spacing, the solution will be approaching the uh, exact solution of the PDE. And third one, it is unconditional stability. So again this is false because it is a conditionally stable system. So first one is true, second and third are false. For a one-dimensional wave equation, which of the following is true for the FTFS explicit scheme? It is the first order accurate, it is true. Second one, it is inconsistency, it is false because it is consistent, because with reduction in time and space grids, we will be approaching the original solution of the PDE. And second one, it is unconditional stability. Like it is conditionally stable, so third statement is also false. Now we will look at the options first. Option A, it is 1 only. Option B, it is 1 and 2. Option C, it is 1 and 3. Option D, it is 2 and 3. So answer is option A, because 2 and 3 is false. A, 1 is true. Which of, for the one-dimensional wave equation, which of the following is true for FTFS explicit scheme? So it is option A, first order accurate only is true. Second and third are false. So answer is option A. A1 is the right answer. So we'll see the answer. FTFS scheme, forward in time, forward in space. So if you are taking it like this, dou u by dou t plus alpha into dou u by dou x. So we are using forward in time and forward in space. So we will get the final equation like this. Yeah. So it is dou u by dou t, we are rewriting is that like this, alpha into dou u by dou x at I and at n. So I is the space position and n is the time position. So we are getting ui at n plus 1th time step minus ui at nth time step divided by delta t plus alpha into u at I plus 1 at nth time step minus u at I at nth time step divided by delta x. So this is forward difference in with respect to time, and this is forward difference with respect to space. Here we are varying the spatial coordinates. Here we are varying the time steps, that is n plus 1th time step and nth step. So delta t and delta x, and this is the truncation error term. So we are using minus delta t by 2 into utt, that is delta d square u by dt square, so those terms, and here d square u by dx square into delta x by 2. So here we are having other terms. So now we can neglecting the terms starting with delta t and delta x. So it is first order accurate. These terms are truncation error. So we are first power of the first terms are like first difference terms are 1. So it is first order accurate with respect to space and position. So first statement is true. So yeah, this is just we are taking the other side, this one the other side, and this we are taking. So as delta t and delta x approaches 0, right? Delta t and delta x approaches 0, error is also minimizing. So we are calling the system as consistent system. It is not an inconsistent system, since with the reduction of delta t and delta x, and as delta t and delta x going towards 0, error is also minimizing. So system is consistent system, and also it is first order in time and first order in space, and it is like alpha we are having, right? If we take it, if we ignore all these terms and we are taking it to the other side, and we do as we did in the last class, I mean last few problems before, we will be having alpha into delta t by delta x, some function. Sorry, sorry. So we will be getting it in some function. So that is a conditionally stable system. So it will be like conditional stability will be in terms of alpha into delta t by delta x. So it is a conditionally stable system and it is an consistent system. So it is first order in time and space. It is a consistent. It is a conditional stability. So out of all three given here, only first is accurate enough. First is true, first order accuracy is true, rest are false. So answer is 14. Answer to question 14 is option A, that is 1. Now coming to question 15, what we have is that which of the following schemes may give assurance of convergence for the unsteady advection equation? Which of the following schemes may give assurance of convergence for the unsteady advection equation? So first one, it is FTBS explicit. Second one, it is FTFS implicit. And third one, it is CTCS implicit. So which of the following schemes may give assurance of convergence for the unsteady advection equation? So here the equation under consideration is unsteady equation and it is an advection equation, and we are given three schemes, that is FTBS, forward time backward space explicit, second one forward time forward space implicit, and third one it is central time central space implicit. So as I mentioned earlier, mostly explicit schemes will be conditionally stable schemes and implicit schemes will be like unconditionally stable schemes. So first one, it is FTBS explicit, mostly it will be conditionally stable, but it will be stable system. And FTFS implicit, if you look at it, and CTCS implicit, both of them will be unconditionally stable. Now next is that we need to check for consistency. So when do we say the system to give assurance for convergence? When the system is stable and it is consistent. So all three systems are stable enough. And now when we are looking for the consistency, what will we say? If delta t and delta x approaches 0, if error is also minimizing, we will call it as a consistent system. So mostly it is an advection equation. So it will be like dou f by dou t plus dou f by dou x equal to 0. In those cases, as delta t and delta x approaches 0, error will also be minimizing. So mostly these three systems will be like consistent systems. And these three schemes will give consistent. These three schemes are consistent schemes. And so all three systems can give assurance for convergence. So since these systems are stable and these systems are consistent, we call it as, we can get convergence from these systems, from these schemes, not systems, from these schemes. So 1, 2 and 3 are right only. Now we will look at the options first. Option A 1, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. Which of the following schemes? So it is option D is the right answer, because 1, 2 and 3 are the right ones. Answer is option D, 1, 2 and 3. So now we will quickly see how equations are discretized for these schemes. So first it is unsteady advection equation, dou f by dou t plus a into dou f by dou x equal to 0, and we have this is in this slide. I am just listing out different schemes and how the equations will look at. So FTCS explicit scheme, so it is forward time and central space. This is not given in the option, so don't confuse yourself. just for the information sake I put it here. So FTCS explicit, so it is forward in time n plus 1 and nth time step, and central in space, so it is I plus 1th grid spacing and I minus 1th grid spacing divided by 2 delta x, and FTFs, so forward in time, forward in space, so F at I n plus 1th time step minus Fi at nth time step divided by delta t. So forward in time and forward in space, I plus 1th grid spacing and ith grid spacing at nth time step. So forward time, forward space. Now if it is forward time for backward spacing, what will happen? This term will remain the same, whereas this particular term will become something like a into f at I at nth time step minus f at I minus 1 at nth time step. So I haven't given, but still okay. FTF is implicit scheme, this is explicit scheme, this is implicit scheme. So what is varying, rather than keeping it at nth time step, we will be using the n plus 1th time step for the implicit scheme, and we will be like taking average also in certain cases wherever required. So, and FTBS explicit scheme, this is what I have been talking about, ith time step minus I minus 1th time step, and central time, central space, we have Fi at n plus 1 minus Fi at n minus 1 divided by 2 times of delta t plus central spacing a into f at I plus 1 minus f at I minus 1 at nth time step divided by 2 times of delta x. CTCS explicit, that is CTCS implicit, where we are using the n plus 1th time step. So why did I jump to one dimensional wave equation? So yeah, this is the diffusion, not diffusion, advection equation. So one dimensional advection, unsteady advection equation. So here sigma, if we are taking it as alpha into delta t by delta x, forward time, backward space, this is what is given in the options, forward in time, backward in space. So we will be having u at ith position, ith position at n plus 1 time step equal to u at I at nth time step minus sigma into ui at nth time step minus ui minus 1 at nth time step. How are we obtaining these equations? These equations we are obtaining from the last discretized equation, like in the last slide we have discretized the equations. We are just rearranging those terms and using sigma as a into delta t by delta x. By substituting this and rearranging the terms, we are getting the value of u at ith position at n plus 1th time step as this. For the forward time, backward space explicit equation, and forward time, back central space, we are getting it like this: ui at n plus 1th time step equal to ui at nth time step minus sigma into ui plus 1 at nth time step minus ui minus 1 at nth time step divided by delta 2. Similarly, forward time, forward space, central time, central space. Yeah. Similarly, for the central time, central space, we have equations, and not this. I'm sorry, but this should be central time and central spacing equations, but I mistakenly used forward time, forward space. But yeah, central time and central space also we can get equation similar to this. So for the unsteady advection equation, like similar to last equation, we have this dou f by dou t plus a into dou f by dou x equal to 0. Forward time, backward space. I'll delete the last slide because it is a bit confusing for now. Like it is like sitting in between. So I'm just deleting it because we are however seeing the equation for the unsteady advection equation. So it is dou f by dou t plus a into dou f by dou x equal to 0, and we are writing it as ft plus a into fx equal to 0. So ft is dou f by dou t, fx is dou f by dou x. So forward time, backward space explicit is given by this fi at n plus 1th time step equal to fi at nth time step minus sigma into fi at nth time step minus fi minus 1 at nth time step equal to those things, and these things are different. So it is just values over here after discretization. So don't confuse with that. That's why I deleted it. So FTBS explicit is given by this. So here we are using I and I minus 1 for backward in space. So FTFS implicit. So we are using I plus 1 and I, and also we are using the n plus 1th time step because it is implicit. So in implicit we will be using the time step for which we are calculating. So here we are calculating for n plus 1th time step. So here we are using the n plus 1th time step as well. So explicit is we are using the nth time step, previous time step. So now it is CTCS implicit. Fi at n plus 1 equal to Fi n minus 1 minus sigma into Fi plus 1 at n minus Fi minus 1 at n. It should be n plus 1. Okay, it should be n plus 1, but let it be for now. So whereas here sigma is a into dt by dx. So in all these three schemes, we are asked to identify which of them will be convergent. So rest of the terms are there, but when delta t and delta x are going to 0, so those terms are also becoming 0 in all these schemes. So we can say that it is all three schemes are consistent schemes. And also here it is conditionally stable, but these two will be iteratively solved. Implicit schemes will be iteratively solved, and so it is conditional stability is not required. These schemes are unconditionally stable. So because we can see that all values are at n plus 1 time step, so it will be iteratively solved at unconditionally stable. First one is conditionally stable. So we can say that it is the convergent system. So it is conditionally stable, unconditionally stable, but all three are consistent. So since these schemes are consistent as well as stable, they will give converged solution. So that is what is asked in the question. Which of the following schemes will give assurance for convergence for the unsteady advection equation? FTBS explicit, FTFS implicit, and CTCS implicit. So all three schemes will give assurance for convergence for the unsteady advection equation. So answer is option D, that is 1, 2 and 3 is the right answer. Now so I hope it is clear. Now we will go to question 16. Which of the following schemes is only conditionally stable for the unsteady diffusion equation? Which of the following schemes is only conditionally stable for the unsteady diffusion equation? So first one it is FTCS explicit, and second one it is Crankford-Nicholson scheme, and third one it is Dufort-Frankel scheme. So out of all these, we need to identify which of the schemes is conditionally stable. So while looking at it itself, we can say that it is first one, that is FTCS explicit scheme. So we know that explicit schemes are conditionally stable schemes. So forward time and central space for the unsteady diffusion equation is explicit scheme, and also explicit scheme is conditionally stable scheme. where it will be condition will be based on alpha, delta t, delta x. So those three things. And second one, it is Crank-Nicholson scheme. Crank-Nicholson scheme is an implicit scheme, so it is an unconditionally stable scheme. And also Dufort-Frankel scheme is also a like unconditionally stable scheme mostly, but it avoids the time step restrictions. It is mostly will be unstable for large time steps mostly. It is like a combination scheme, so it is complicated system, so we can directly say that it is first one, that is FTCS explicit scheme. So option A 1 is the right answer. Option A 1, option B 1 and 2, option C 1 and 3, option D none of the above. So option A is the right answer. FTCS explicit is the right answer. So diffusion equation is given by dou f by dou t equal to A into dou square f by dou x square, and FTCS explicit is given by f at forward time and central space. So fi at n plus 1 minus fi at n divided by delta t equal to A into f at I plus 1 at nth time step minus 2 into fi at nth time step plus fi minus 1 at nth time step divided by delta x square. So it is forward time central space explicit scheme. Similarly, Crank-Nicholson scheme equation is given by this: fi at n plus 1 minus fi at n divided by delta t equal to A into average of this Crank-Nicholson scheme. We take average of n plus 1th time step and nth time step. So it is fi plus 1 at n plus 1th time step minus 2 fi at n plus 1th time step plus fi minus 1 at n plus 1th time step plus fi plus 1 at nth time step minus 2 times of fi plus fi at nth time step plus fi minus 1 at nth time step divided by 2 times of delta x square. And Dufort-Frankel scheme is again average of n plus 1th time step and n minus 1th time step for nth time step. So we will get the final equation as something like this: fi at n plus 1 minus fi at n minus 1 divided by 2 times of delta t equal to A into fi plus 1 at nth time step minus fi n plus 1th time step minus fi at n plus 1th time step, both are same, plus fi minus 1 at nth time step divided by 2 times of delta x square. These equations, when we are referring, please refer once with textbooks, because might be I might have made some mistakes while writing. So concepts make sure you can use, but equations just check once. So Dufort-Frankel scheme, so it is conditionally stable is FTCS scheme is conditionally stable. FTCS explicit scheme is conditionally stable, and if Crank-Nicholson is unconditionally stable, and Dufort-Frankel is also unconditionally. It mostly will be like unstable at large time steps. So that is it. It is not unconditionally unstable, but unstable at large time steps. Now we will see question 17. In question 17, what we have is that which of the following schemes is second order accurate in both time and space for the unsteady diffusion equation? Which of the following schemes is second order accurate in both time and space for the unsteady diffusion equation? Forward time central space, and second one it is Crank-Nicholson scheme, and third one it is Dufort-Frankel scheme. So it is asking regarding second order accurate in both time and space for the unsteady diffusion equation. So these Crank-Nicholson scheme and Dufort-Frankel scheme is actually second order accurate in time and space. When we saw the equation itself, we were seeing that. Whereas forward time central space is second order accurate in space, but it is first order accurate in time. So it is first order accurate for the time. So it is false. Whereas 2 and 3 are second order accurate in both time and space for the unsteady diffusion equation. In the first one, it is second order accurate in space but first order accurate in time. So it is false. So options are option A 1, option B 1 and 2, option C 1 and 3, option D 2 and 3. So which of the following schemes is second order accurate in both time and space for the unsteady diffusion equation? So answer is option D, that is 2 and 3 is the right answer. Option D is the right answer. Now we will go to question 17 explanation. Diffusion equation, unsteady diffusion equation is given by dou f by dou t equal to a into dou square f by dou x square. Forward time central space explicit equation is given by this, and for Crank-Nicolson scheme equation is given by this, where it is an average of n plus 1th time step and nth time step, and Difford-Frankel scheme is given by this. So except except FTCS explicit scheme, Crank-Nicolson scheme and Difford-Frankel scheme are second order accurate in both time and space. So that is it. Which of that for question 17. So now moving to question 18, what we have is that which of these properties is not included in the Lax equivalence theorem? Which of these properties is not included in the Lax equivalence theorem? So option A, it is stability. Option B, boundedness. Option C, consistency. Option D, convergence. So we know the answer as boundedness actually. So how it is, like, what is Lax equivalence theorem stating? Lax equivalence theorem is stating that stability and consistency are enough criteria for the system to be converging. When we want converged solution, we should ensure that the system is that the schemes we are using is stable schemes, and we will be getting consistent solutions. So when stability and consistency are ensured in the system, convergence is also ensured. That is what is stated from the Lax equivalence theorem. So we are having stability, we are having consistency, we are having convergence. So option A, C and D are included in the Lax equivalence theorem, but option B is not there. Boundedness. What does boundedness mean? Boundedness is within the range. Like in certain cases, for example, if temperature value is given, we are estimating the temperature within the system wherein we are heating it, but mostly it will be within certain range, right? It would be like, when we are heating, it would be like a minimum temperature would be so and so, and maximum will be so and so. It would not, the minimum temperature would not fall below certain degrees when we are heating. So unless any external source term is involved in this equation, involved in the system. For example, when we are heating it or when we are cooling it, the temperature variation we will be able to observe. But when we are not heating it or when we are not cooling it, that temperature variation we will not be observing in the system. That is one example for boundedness. And also when we are heating it, we will be able to see increase in temperature, but fall in temperature beyond a certain value we will not be seeing. So, and also velocity values and certain parameters like void fraction, volume fraction, those parameters when we are solving, it will be above 0 and less than 1. So we are having certain bounds for those parameter values. So that is what we call it as boundedness. When we are solving for those variables, the values should be within that bounded ranges. So that is what we mean. So boundedness is that, but boundedness is not included in the Lax equivalence theorem. In Lax equivalence theorem, what we are seeing is that stability, consistency and convergence. Only these three we see in the Lax equivalence theorem. we do not see about the boundedness. So question 18 is that. Answer to question 18 is option B, boundedness. Now coming to question 19, what is asked? A solution is ideally converged if dash. A solution is ideally converged if dash. Option A, the results match with the exact solution. The results for two consecutive iterations are the same. Option B, results for two schemes are the same. Option D, results for different boundary condition are the same. So actually, like if it is converged if two consecutive iterations, if we are getting the same solution, so we'll see the statements one by one. First one, it is mentioned that results match with the exact solution. Results will go closer to the exact solution of the partial differential equation. That is, the computed solution will be moving closer towards the exact solution of the partial differential equation, but it will not be matching in most cases. So that is not the case. So A is false. B is results for two consecutive iterations are the same. If we are getting the same solution in the two iterations, we will call it as a converged solution technically. But mostly we will allow it for certain number of iterations to get the same solution. But if two consecutive iterations we are getting the same results, we technically it is a converged solution. And third one, it is results for two schemes are the same. Mostly between two schemes results won't be same, and even if they are same, it won't make any we cannot make any thing out of it. So results for two schemes are the same, like values will be a bit different, but if schemes are perfectly aligned with our problem in question and we are getting exact solutions, results from two schemes would be almost same. And finally, results for different boundary conditions are same, that we cannot obtain actually. Results vary with respect to the boundary conditions. If temperature is given certain values in one system, and for example it is 273 Kelvin in one system and 500 Kelvin in another system, obviously results will not match, and we it is not related to convergence as well. So answer is option B, results for two consecutive iterations are the same. Now moving on to question 20. What we have is that in real, how is convergence defined? Again and again. Okay. In real, how is convergence defined? Similar to last question. Variations are accepted when variation is less than the result. Option C, when variation falls below a certain acceptable range. Option D, when variation is same as the result. So when we are dealing with practical CFD problems, right? When you are solving pipe flow system, or when you are estimating temperature of heating rod or something, what at what stage we say this solution is converged? Like in reality, in experiments we can see something and we can estimate something, but when we are using CFD, right, and the variations will always be there mostly. So variations are accepted, is it true? Like, but variations will be there, but at what condition we are accepting the variation is there? It should be like, in some cases it will be like 10 power minus 8, 10 power minus 9, so that variations will be there. But it is like 10 power minus 1, that variations are not accepted. So like 0.1, 0.2 difference is huge. I'm talking about in the 10 power minus 6, minus 7, those scales. So how is convergence defined? Variations are accepted. Convergence has nothing to state that variation is being accepted. So option A is false. Option B, when variation is less than the result. Variation and result, variation is difference. like result should not match, I mean variation should not be compared with the result first of all. So option B is false. Option C, when variation falls below a certain acceptable range, this is true because like we are, as I mentioned, it is less than 10 per minus 6, 10 per minus 7, so we are giving some range. When variation falls below a certain acceptable range, so we are saying it is convergence. In last problem also we have seen that between two consecutive iterations, if it is the variation is less, we are saying it is convergent. That variation is like less than this, less than that, we are giving certain acceptable range. So that is how we define it. So option C is the right answer. And looking at option D, again it is variation same as the result. We cannot compare variation with the result, so it is false. Option C is the right answer. 19th answer once again. Okay. A solution is ideally converged if dash. So option results match with the exact solution. Option B, results for two consecutive iterations are the same. Option C, results for two schemes are the same. And results for different boundary conditions are the same. Uh, so it is like when we are saying solution is converged, if results between two consecutive iterations are same, we call it converged. Like that variation should between the two consecutive iterations. Like in CFT, we will be solving it based on iterations. Like it will be, we will be giving certain number of iterations or certain conditions. Like if value variation, that is if for example if we are calculating velocity and we are saying that one scheme will iterate over and over at particular time instant, and when we are observing variation between two velocity value between the velocity values in the time steps, and we are seeing that it is 0.1 in one 0.1, and in the next iteration we are having 0.99999. So we are having 10 power minus 6 variation or 10 power minus 7 variation, so we will be giving something. So if that that is the case, we will say solution is ideally converged. So results for two consecutive iterations are the same, solution is converged actually. Option B is the answer. Okay. Now we will go to question 20. Yeah, 20, as we have seen, it is about in real how is convergence defined. It is about variation is less than certain acceptable range. So when the variation falls below a certain acceptable range, we say it as converged. So option C is the right answer, when the variation falls below a certain acceptable range. Now moving on to question 21, we have which of these statements is wrong? Option A, convergence is applicable for iteration process. Option B, convergence is affected by accuracy and efficiency. Option C, converged solution do not vary much with further iterations. Option D, converged solutions are exact. Okay. As I mentioned, convergence is applicable for iteration processes. Yeah, we use that. And it is affected by accuracy and efficiency. This is also true. And converged solutions do not vary much with further iterations. That is again true because we call it converged when the variation is below a very low value. And last solution, converged solutions are exact. So actually it will be closer to the exact solution of the partial differential equations, but it won't exactly be the exact solutions. Like it will be as close to the exact solution of the partial differential equation, but it won't be the exact solutions. So option D is the answer. That is, converse solutions won't be exact solutions. It will be closer to the exact solutions and with very small variations will be there. Now going to question 22. What do we have? Which of these iterative processes is unstable? Epsilon n is the error in the nth iteration. Which of these iterative processes is unstable? And epsilon n is the error in the nth iteration. So option A, epsilon n plus 1 divided by epsilon n equal to 0.5. Option B, epsilon n plus 1 divided by epsilon n equal to 0.75. Option C, epsilon n plus 1 divided by epsilon n equal to 1.25. Epsilon n plus 1 divided by epsilon n equal to 1. So epsilon n is nothing but error in the nth iteration, and similarly epsilon n plus 1 will be the error in the n plus 1th iteration. So we have 4 options and we need to identify which of the processes is unstable. So in unstable process, what will happen is that variations will keep on growing. So that is what we call as unstable process. Here in 4 cases, it is the error in the n plus 1th iteration divided by the error in the nth iteration. So what it means is that error in the n plus 1th iteration should be less than or equal to the error in the nth iteration. So it basically should be less than or equal to 1. So that is the condition. So now if we look at 4 options A, B, C and D, in option A it is less than 1, option B also it is less than 1, option C it is greater than 1 and option D it is equal to 1. It is less than or equal to, so option D is also acceptable. But option C it is greater than 1. What does greater than 1 mean? Error in the n plus 1th iteration is greater than the error in the nth iteration. So error is growing, keeps on increasing, it is error is growing. So it is an unstable process. So option C is the answer. Error in the n plus 1th time step is greater than the error in the nth time step by 1.25 times. So it is unstable process. Which of these iterative processes is unstable? So option C is the right answer. Option C, epsilon n plus 1 divided by epsilon n equal to 1.25. So going to question 23, we have, which of the following statements is false about the numerical errors? Option A, they are inevitable. Option B, they can be controlled. Option B, they can be eliminated. Okay, we have 3 statements and we need to identify which of them is false. First one, it is they are inevitable. Numerical errors, when we are using, if we are getting the exact solution to the partial differential equation through analytical means, that will be the exact solutions. But since we are using the numerical means, we are just simplifying the solution by converting the partial differential equation into algebraic equations and we are solving these equations. So whenever we are simplifying, there is like some truncation error or some numerical errors which are being introduced. We cannot do anything to avoid those errors. So when we are using the numerical schemes, like when we are using CFD, they are inevitable. So one is true. Second one is they can be controlled. So they can be controlled, yeah, they can be controlled by adjusting the time step or adjusting the time grid spacing. We can minimize the errors, like we can have a check on that error and we can ensure that it is below critical value and it is minimizing. We can control those errors. So second one is also true. Third one, it is stating that they can be eliminated. This is false because we cannot do anything to eliminate those errors because we are simplifying the partial differential equation into linear algebraic equation through numerical schemes, and also we are when we are using Taylor series schemes, we are not using the all the terms. We are just taking the few terms and we are neglecting the other terms, and it is like first order, second order, those things. We are not fully using those, so we cannot eliminate that, but we can minimize that error. So 3 is false. So answer is option A, 1 only. Option B 2 only. Option C 3 only. Option D neither one. Actually it should be both 1 and 2. But yeah, answer is option 3 only. Option 3 is false. 3 only is false statement. Now we'll go to last question for today's session. Okay. In von Neumann analysis, the solution is expanded using dash. Option A Lorentz series, option B Maclaurin series, option C Taylor series, option D Fourier series. So when we are using von Neumann stability analysis, right, how we were expanding the solutions, we were using the Fourier series to get that stability analysis. So the solution is expanded using Fourier series. Option D is the right answer. So that's it actually for today's class. Thank you so much. So now if you have any doubts, you can ask. Okay, thank you so much for joining, and yeah, it was, thank you. We'll meet again next week at the same time, 3 p.m. to 5 p.m. next Saturday. These presentations, I mean these slides and videos are will be available to you, so you can use them whenever required. So yeah, thank you so much. We'll meet again next week.